audio might be a little bit silly here. Okay. All right. If people can hear me, please give me a thumbs up. Great, thank you. Let's do this. Seems we're ready to roll. Not sure if I started the recording with someone else. Yeah, great. So, yes, we're going to continue our journey into graphical models. And for the third and the last lecture. So today's lecture will be a little bit abstract. So we're going to spend time in breaking down a number of basically recursive constructions mainly. So before that, let me just say that, well, please come to the guest lecture. And I hope those of you, I can see some of you online now and also last Wednesday who are actually on campus. So if you can come meet our guest speaker and ask him questions. So questions can be technical, but also about careers in machine learning and their applications of machine learning. I think it will be exciting. So see you there. Some of you already attended graphical model tutorials, so those will be on this week and next week. So traditionally there has been one graphical model tutorial, but there is lots of content, so we break it up in two. Hope you're going well in assignment. It's this time of the semester. I know everyone is a bit busy. Our final exam has been announced, so it will be like held early in the exam cycle. So hopefully that gives you enough motivation to just study and then get done with this class. I know it's hard, and then you can focus on also the other classes. More instructions will be posted later or soon on Piazza. Watch that space. So this is what we are going to talk about. So as sort of hinted in the first graphical model session, we are covering three types of graphical models, and the last type is called factor graphs. It's an interesting and flexible representation, and the goal of introducing factor graphs is to cover inference procedures, which we kind of sort of shoved aside at this moment, besides using, say, Bayes rule. We know that it's on large graphs, this is hard, but some product algorithms, a very conceptually clean way of thinking about inference in tree structure factor graphs. And you might also be happy to know that factor graph and the sum product algorithm was proposed in the late 1990s. So in Brendan Frey's paper and also in his the paper he co-authored with Frank Kishnan, both of them are faculty members at University of Toronto right now. The second one is a journal paper. It was basically written just before year 2000 and published in 2001. So for most of you, this will be roughly sort of within your lifetime. And it is also to say that, well, for perspective, there has been lots of things happening in machine learning before the deep learning resurgence, let's just say that, or neural network resurgence. This is one of the recent innovations. So there were a number of other development that were sort of 10 years before that in terms of Bayes nets and graphical models, and yeah, we might touch upon these. But I felt like the historical note also helps people put things in perspective. I would say, right, the big breakthrough in machine learning around year 2000 is this one, and the big breakthrough say right after, for about 3 to 5 years, are support vector machines, kernel machines, and the theory and practice of that, right? And then when it inches close to 2010, people were already talking about deep learning programs. I remember there was a DARPA program that people could bid for. Where I worked at that time, we did bid for it, but we didn't succeed because, of course, we didn't know as much as people who were working on neural networks for 30 years. So there were like latent trends that are sort of incubating towards the next big thing. So, all right. So factor graph is yet another representation of graphical models. It can be converted, right? So there are ways to convert essentially factor graph with undirected graphical models, as we talked about. But it has its own set of languages too. So the goal here is still to represent a joint distribution among a set of variables, p of x, denoted. And here we represent it with a product of factors rather than potentials or conditional probabilities in the other case, right? So let's say we simply denote it as like each factor is called f sub x s of x sub s. The sub s business refers to simply a subset of variables. For example, the p of x in this simple factor graph here, or simple 3-node graphical model here, is represented as, can be represented as a factor about x3, a factor about x2 and x3, and a factor about x1 and x2, actually two different factors about x1 and x2. You might ask, oh, why bother? Yeah, why do we want to do this? So what this expression says is roughly between x1, x2, and x3, there is a link between x2 and x3. There's a link, well, if we think about it in an undirected graphical model lingo, x1 and x2, right? So if this were an undirected or Markov random field, then these two factors involving x1 and x2 would be in one potential function. They would be known as, let's say, psi of x1, x2, and this book denotes it as like with the clique subscript. So what would be the advantage of having these additional factors? It could be, well, if we were talking about physics or, for example, then these different factors can represent essentially different physical intuitions. Let's say we're modeling the weather in the natural world and maybe the performance of our solar panel or and surrounding components. Let's say like one of the factors could be related to humidity. And one of the other factors could be related to, say, temperature. So being able to think about them separately and model them separately sometimes has sort of an advantage. Of course, you could separable, basically a multiplication of two different terms as well. I think it comes handy when, especially handy when some of these, maybe some of the measurements are sort of the reliability and availability of different measurements are different. And it's always good to have different way of representation as sort of army of like a chest of weaponry that we could draw from. All right, so how does this relate to directed graph, right? So we could, so we can see that if we have a factorization in the base net, we can trivially convert it to factor graph by just calling, like having a factor for every node and all of its parents, right? As we say that for undirected graph, that a potential function over clicks, over maximum clicks, readily converts themselves, lends themselves to factors. Then you say, well, what about Z? It is a normalizing constant, and we can treat that as a factor too. It's just over an empty set of variables. This is to say that factors are unnormalized. In the same way that potential functions are unnormalized. Yeah, they are usually non-negative. It will be good if they are strictly positive, but they are not probability distributions, unlike the conditional probabilities. Okay, we have been mainly talking about factors. Let's look at a few examples before we talk about the graph a bit. As you can see, the additional flexibility means that we can end up with different factor graphs representing the same distribution. So this is a little Bayes network representing the head-head pattern that we struggled with. We can basically convert this to a factor graph of 3 nodes and 1 factor. Or we can say, we actually have additional knowledge about maybe the prior of x1 and x2. So we create 2 additional factors for each of them. So indeed, the factor graph B with the factor, or a factor is a function over values of the nodes, right? And this function is simply a factorization according to Bayes rule. And in the representation C, when we're teasing this like factor or potential term for x1, x2, x3 apart, we actually resemble what was done in Bayes net. We have essentially a prior factor that's only connected to 1 node. All right, I hope that's clear enough. So the factor graph are what's called bipartite graph. For those of you who have seen graphs, this is a refresher for those of you who haven't seen. So a bipartite graph is a graph whose vertices can be divided into 2 disjoint sets, such that all the edges are between set U to set V and not within set U to set V, or set V. So in the case of factor graph, so these are variables and these are factors. So as you can see, this is sort of a way of, like the way of thinking about graphical model has changed between the directed and undirected graphical model, where we're explicitly talking about relationships among different variables, which can be more intuitive to think about in specifying the dependency and real world knowledge, right? So Bayes net and MRF, like they're intuitive to think about like variable dependencies. So we argue that factor graph is better for thinking about inference. Constructing. So what we do here for, let's say, undirected graph is to create a node, create variable nodes for each node. Okay, now extra work is done. And then we can create factor nodes for each maximal click. And then we set the factor potentials. That's basically just a different way of looking at like the same undirected graph. You may ask, what happens for directed graph then? So for BaseNet, you go through the procedure we call moralization, pardon the name, into a undirected graphical model, and then convert it to a factor graph using this. Okay, easy enough. We've been kind of saying that graphs with loops are bad for inference, and graphs with trees or chain structures are good. So let's just sort of keep that in mind and look at what factor graphs are like and inference. Before, like after we have covered the inference procedure, hopefully we'll understand a bit more about why trees are good. But for now, last Wednesday, we sort of ended our discussion on MRFs with polytrees. I was being a bit vague about what polytrees are good for, right? Because if we directly convert them into an undirected graph, obviously there's going to be loops because of this head-head patterns. But what is helping here is that if we use the factor graph representation, the resulting factor graph is actually a tree. So factor graph are bipartite, undirected graphs. So it's easier, like quote unquote easier to have trees because there are by definition no nodes between the variables, right? So these links are gone. Instead, it's replaced by a factor with links to all three nodes. So additional cost we pay here is, before this we have a 5-node network. Now with the factor graph, we have at least 7 different nodes, but in this particular case, we have 5 plus 5, 10 different nodes. That's a representation complexity to pay in order to end up with a tree and something we can, like some data structure we can use to do inference. Here's another directed graph with the head-head pattern and also with another edge, right? So if we treat this as a base net, we essentially have no representational savings. Basically, like this is a fully general factorization of the joint probability. If we treat it as MRF, there's also no savings. Psi is actually over all the variables, and it's equal to f of x1, x2, and x3. But as you can see, factor graph can Right. Once we convert it to a factor graph, it is tree structured, right? This or the undirected version, right? So this original Bayes network is certainly not tree structured, but the factor graph is. You might say, oh, what is the free lunch? Is there any free lunch to be had? Computational advantages that we can have for free just by using the factor graph? The answer is actually no, because the bottleneck for inference is the size of the clique. Can revisit this point, or you can remind me towards the end. So you may ask, is factor graph always tree structured? The answer for that is also no, because you can construct factor graphs, let's say for the same undirected graphical model, right? So this undirected graphical model is actually the undirected version of the one on the previous page. If we do it like this, it's tree structured. If we do it like this, it's not tree structured. It has loops, undirected loops. So what does this say? It does say that we can make factors that does not correspond to any conditional independence properties. If sometimes there's a good reason to do this, but for now I would say, okay. So factor graphs with loops, let's say bad for inference, as we can see after we go through the sum product algorithm. So yes, you can make it many different ways, but there are better or worse ways of making factor graphs, just because it's so flexible. All right, so we have gone through what factor graphs are and roughly how to make them. And we have given you some prior heuristics without justifying why factor graphs with loops are bad. Basically, try to make them so that they are trees, bipartite trees. So we're now going to move towards the sum product algorithm. Which is the main content of this session. The goal here is to evaluate local marginals over nodes or a subset of nodes. An example of this is, let's say we have the joint distribution probability of x1, x2, x3, and x4, and then local marginals is, if we want probability of x3, what should we do? Given all the conditional, well, the graph like parameters, or if we want probability of x, the joint probability of x2, x3, and x1, what do we do? Or do we, if we want probability of x2 given x3 equals 1, what do we do? Right, so this is the most general case. A related case that's also in the book, but we are not gonna cover in this lecture, is to find the most probable state. This can be done by a simple tweak of the sum product algorithm that we'll cover. And finding the most probable state is, in practice, a very useful question to ask about graphical models. So what are some of the applications? So for a long time, speech recognition is done by graphical models, especially the subclass called hidden Markov models, basically graphical models over time, over a sequence of symbols, sequence of actually speech observations And the recognition part is actually done by finding the most probable state, right? Given that the machine has heard this waveform, or given the set of possible phonemes, what is the most probable words that are being said, and what is the most probable sentences that are being said? So that's done by like this max sum algorithm. Um, how is it done today? So speech recognition is done by, well, neural network in the sequence nowadays. Some version of this is still in use, right? So the argmax of operation are everywhere. Um, in language models, in speech recognition, in any of the, like if you're talking to your phone, talking to your smart speaker, but sometimes it does de-emphasize sort of the role of the entire sequential history. It usually does some sort of limited memory Viterbi decoding. Anyway, so for convenience, we are going to work with all the graphical models as if all variables are discrete in the lecture. So therefore, when we say sums, this can be generalized with integrals over continuous variables. We are not going to cover this in the lecture, but in things like the exam, you might find yourself having to do one, like, or maximum 2 levels in integral. That is to say, I do not necessarily recommend to you to go and study chapter 13 yourself, but just bear in mind the principles that we introduce. Right, so a little more on this historical note, right? So this algorithm is very similar, or actually it is also called belief propagation, before the factor graph representation was introduced. So that's a decade before the factor graph work. It does perform exact inference on directly acyclic graphs or Bayes networks. Right. And then 10 years later, this alternative representation came about, and it's more general. It applies to any. So just as a quick recap or reminder of one of the dense slides of last Wednesday, the reason we're introducing those is also to preempt like the sum product algorithm, right? So remember what we did last time for a chain-shaped graphical model. Remember, we also were computing what we call messages, mu of sub alpha and mu of sub beta. So alpha and beta refer to the forward and backward messages in sequence models, but they, well, here they were just some notation to distinguish things. And alpha and beta, mu of alpha and beta are computed recursively. They also represent basically a marginalization of potential functions over different variables, where we essentially shift where we do the sum in order to save or be computationally efficient, right? So if you have understood that part last Wednesday, so with that in mind, we can sort of use it to look at the next section. If you haven't, then don't worry, because we're gonna go through similar, like very similar things again. So the basic mathematical foundation of the sum product algorithm is what the distributive rule of multiplication, which is what we have learned in what, 5th grade or 3rd grade. I don't know which where it sits in the curriculum right now. So what it basically says, right? So as computer scientists, multiplications are expensive. Summations are less so. So by doing this, by doing AB plus AC equals A multiplied by B plus C, we essentially try and do the summation. So there are two key ideas. do the summation first, or when we can. And then multiply less. So in this particular case, it's 2 multiplications down to 1. All right. So here's a bunch of notations and a bunch of figures from the book that help us understand this thing. Right. So the stuff in green we already know about, right? The second thing in green is simply the definition of factor graphs. Let's say we are concerned with, so this lowercase x non-bold is this one variable where we want the marginal of it. Marginal distribution of x. This is sort of a small probability table of essentially, p of x and then value of x, right? Say 0, 1, 2, k. And we're expected to essentially fill this little condition, marginal probability table. In the fully general form, we can simply say we take the join of p of all the variables, x bold, and then we sum over all the other variables except this variable we care about, little x. And this is obviously order of k n minus 1. That's bad. And we can then simply plug in this factor graph definition, saying that the join is actually the sum over factors of the factor terms of subset of nodes that it goes through. So right now we haven't done any work. There is no savings. The first thing we do is to rearrange this general factor graph factorization into neighborhoods of the node we care about, x. So imagine a big tree-shaped factor graph. Let's say for now our factor graph is a tree. The property of a tree, especially undirected tree, the nice thing is actually you can take a node, essentially use it, like treat it as a root, basically shake the tree, pretending you're holding the node. Then all the other node will just fall below it and it's still a tree. That's sort of a hand-wavy thing of saying it, but officially speaking, right? So if this were undirected or directed tree, right? So you might have to turn some, like, so each node has exactly one parent in the tree, right? So for undirected trees, you can just treat which, like sometimes flip the parent-child label, but you still have a tree. So given that, right, so we introduce a whole bunch of new notations. Let's just go through them a bit slowly. So the neighbor NE of x is neighboring factor nodes. So you say, hey, what? So because the graph is bipartite, the neighboring nodes of a variable node is only factor nodes. Right. So these, they are in NE of x. So when in this sort of bipartite tree, what we expect is actually something like this, right? So we have x, and then it has a bunch of let's say, children nodes. They're all factors. And then each of them have a bunch of children nodes. Each of these are now like variable nodes, and it goes on and on, right? What this means is, in order for the factor graph to be a tree, right, each variable can, like, they are associated with one factor, and then, right. So that's the way recipe of making a tree, right? Which is also to say that if we put each variable in its max clique, it will have that particular factor. So that's intuition, right? So, and so we have x, we have the next level, which is ne of x. And then we have the next level is the set of x, big X sub s, which means the set of nodes, the set of all variables in the subtree connected to the variable node via factor node f of s. Right, so in here, the subscript s refers to a particular factor node, right? So let's say this is f of s, and these two will now be x of big, small s. All right, and finally, the final notation is this one. As we can see, we've talked about the node, the factors, the node connected to these factors. Then now we need to talk about basically some factors again as computation, right? So factors are functions. So the big f of s, comma x, comma big x sub x is the product of factors. I know this is a mouthful. The product of all the factors in the group associated with factor f of s. So this is a mouthful, but visually speaking, what this means is, if we look at the factor f of s, this big f sub s is basically the product of factors in this light blue cloud. From all the nodes, yeah, basically all the factors that contribute to f of s. All right. So with these notations, we can now rearrange the p of x as a product over simply the last term. What does this mean? It means for this figure 8.46, what we're looking at is essentially p of x, the entire join centered on this new root node little x is simply a product of a term related to each of its factors, f of s, and then this is f of x2, f of s3, and so on. So that is to say, this big F is a product of little small, some set of small f of s. And which one it is basically we arrange it according to this tree. Right? What that means is it would include f of s and all the other factor nodes hanging downstream as descendants of these x of s nodes. All right, I hope that's good enough for now. I'm gonna see them again. So let's do this. So it is worth noting in this notation, use a different color, right? So union over x of s, like s over neighborhoods of x is equal to basically this all the variables minus the little x that we're looking at. So hopefully that's obvious based on this little tree structure we drew. So that means the marginal distribution equal to essentially, right, because the joint distribution is a product of these big F's. The marginal distribution is therefore the product of these big F summed over all the other variables. Because these, and also because the way the factor graph is organized, it's a tree, so the intersection between one set of downstream variable nodes with another set of downstream variable nodes is empty. Therefore, we can move the summation sign inside and just sum over each of these big F. Okay, I hope you're still following, right? And this being able to move the summation sign inside is sort of in the same spirit as what we did with chain graph last time. We'll see this again. And once we have done this, we are just going to rename these mu term, like this sum over these big F's as a mu term. And we call it the message mu from this factor node F small s to the node X. Okay. And it's nothing but essentially these big F with all the downstream nodes marginalized out. All right, I hope we're happy. So let's move on with an example. So on the upper right hand side is what we just saw. Because there's a fair bit of notation, we're just gonna we're repeating them on this page, right? So the marginal probability of on the variable little x is a product of these messages, where each message is actually a marginalization of the product of other messages or other factors, big F, over all the nodes downstream of factor S from anchored at like little x. That's definitely a mouthful, but let's do this, right? So for our 4-node simple graphical model, we construct a tree-shaped factor graph by essentially just place a factor on each edge. Actually, this is a good trick for constructing factor graph for graphical models that are tree-shaped to begin with. What's happening here? Go away. Okay. So there are 3 factors, and if we want to compute the marginal of x2, as we can see, we shake this centered or rooted at x2. The first level siblings as the 3 factors, and then the 3 nodes as the second level offspring, right? So the first line is nothing but just the definition. We marginalize over all 3 other variables over all factors. And then because factor A, the downstream nodes from factor A only involve x1, we can essentially use that formula 8.64 and pull x1 to, like, when we sum over x1, the only relevant factor is only f of A. Okay, so that's the first mu. Oh, yes, that's the first mu. Let's see. We write it, this will be mu of fa 2x valued at x2, or x2, right? Similarly, the second factor f of b is only involving, it's the factor involving x2 and x3. So this is mu of b2 x2, which is a function of x2. So the same goes with the last term. So this is sort of a simple instantiation of basically what the downstream nodes XS is, and then what this big F term is. In this particular case, the big F term is simply one, it's simply one of the factors, and that's simple. And this, right, so this also sort of gives us an intuitive sense of the visual mapping between the factor graph and these somewhat abstract term of big X and big F. All right. But in general, you say, what about these big F when the graph is not just 2 layers deep, right? Right, we do need a set of new terms, but let's just, focus on them, like staring them a little more, right? So on the top, what we have is figure 8.46 again. We saw this, right? So there's X F of S and a big F of S and then big X of S. So we now want to expand this green circle or green loops to see what goes into computing this big F, right? We also just reproduce in green the definition of big F and big X in case we forget. So what we want to do is to factorize this factor subgraph. Right? What we have is, we have this subgraph discarding all the other factors. So let me also try to do this. Let me copy this tree. All right, try and copy this tree. And paste it in here. So what we're looking at here. Okay, forget about the neighborhood of X because right now we're zooming into this factor and the subsequent X of S. This page we're looking at this, and this. Yeah, and all the subsequent ones. So the other subtrees we assume can do the same thing to them. Right. So if we factorize this subgraph, we can write it as follows. We know that because each factor node corresponds to one factor in the original factor graph definition. So we first need to write out this factor. Assume it's connected to M nodes, then it's a factor of sub S, X, right? So it involves the original node X, and also involves maybe M other nodes. So it's written up here. And then what it involved all the downstream factors that are connected to each of these nodes. M, right? So let's say there's a factor here, there's a factor here, there's a factor here. And this one might have its own set of factors too. So we use the notation G sub M to denote essentially like all the factors connected to node M. And we need some more of these bit cumbersome but necessary notations. So we have neighborhood of F of S. This should be think, intuitive, which refers to the nodes on the left of f of s plus x itself, right? And then also neighborhood of f of s minus x. So these include just like the nodes on the so this will be neighborhood of f of x minus x. Okay. So these are just notations. And now let's compute the message, express the messages in terms of these terms. It is so. Yeah, okay. So the message we had before, mu of fs. So this message that's being sent to the node in question x is marginalized over all the other nodes, x1 through x begin. It consists of 8.65. Basically, plug in this f of s term, multiplying these g terms. So the notation here, right? Big X of xm is basically referring to nodes that are grandchildren of xm, right? Whereas these are grandchildren nodes of the original node x. And we call each of these factors basically messages. So these are like, we rename the sum of the g terms and call them essentially node to factor messages. So before we had factor to node messages. So now what we have done is that we have defined node to factor messages as basically sum over all the downstream nodes here where we haven't drawn them, the product factor, well, the g terms, and then we express the factor to node messages as a combination of the factor sitting on the factor node and these node to factor messages. All right, we haven't really defined what the G's are. Let's go there. So, yeah, just remind ourselves at this point, after all this notation and two somewhat like really busy figures, what we have defined is two different kinds of messages. So factor to node messages is a sum over these big F terms. And node to factor messages is a sum over these big G terms over the grandchildren nodes of the like the node X. Actually, yeah. So in order to compute the factor to node messages, we take the product of incoming messages along all the other links. well, basically, in order to compute this factor to no message, which is itself a function, we take a product of the no to factor messages, like this product is here, and then multiply by the factor associated with that node, which is this term. Let's number these. So step 1, step 2, step 3. Actually, they are executed in not necessarily that fashion. So take the product. So step 1 here, step 2 here, and then marginalize over all the variables associated with the incoming message. Step 3 here. So just remind ourselves of the factor graph trees rooted at X. So a node is ready to send its messages to the parent node once all the nodes below it have sent their messages. All right. So for those of us who have seen at least one recursion before, so hopefully this looks familiar. If not, it takes a little bit of time to grasp. But yeah, go at it. Yeah, look at it a few times and it will make sense. So this is a summary of the key theorem from Kishan and Frey's 2001 paper. Yeah, Qingyu, we'll get to that. Thanks. In a little bit. So it basically says, right, no to factor messages is a product of the factor to no messages, simply. The factor to no messages is more than a product of the no to product messages, but we need to add this factor term and do this additional marginalization. And then the node marginal is simply the product of the factor to no message. So this sort of spells out how to end this recursive sum product algorithm. We might say how to stop. Here we go. And hopefully this helps with the question that Qingyu just asked. Good question. So we consider node X as the root node, and then we start from the leaf nodes. If the leaf node is a variable node, then we initialize these node to factor messages as 1. If the leaf node is a factor node, then it's simply that factor. So let's go at this for one more time to make sense out of these g of x, right? So with this in mind, let me see if I can. Right. Oh, got this wrong. Can we take a screenshot? That's kind of bad. Copy. So this is from Frey and Kishan. These G terms, they are, okay, the sum of the G terms are no to factor messages. So, right, if the nodes end here, of course, that you use the initialization procedure to say that the node to factor is 1. If they're the nodes are like the nodes are not leaf nodes, then you use this particular, right? So you multiply the factor to no messages to get the G term. Does that? Yeah, what is missing? This is, right. So comparing the free version and the book version, right? So this expression is a useful one. Basically, so if any of these xm is not a leaf node, then I essentially multiply the G term is a multiplication of the incoming factors from the factor nodes, right? So each of this will have a mu of some factor to some x of m. And I multiply these messages to get the G term. I hope that helps. So recursion, yes. So multiply incoming no to factor messages and the factor and marginalize to get the factor to no messages, and then just multiply factor to no messages to get the no to factor messages. That is a mouthful. And well, if we're computing a marginal, by definition, it's a set of ink, right? So it's sort of each children is a set of factor to no messages. So we just apply the first recipe to this. We walked through how to start. Now let's look at our example again. And then if it's still a bit confusing, we can just go at it maybe a little bit differently again. So there we go. We looked at this simple factor graph a bit before. Now let's just write out the whole thing, right? In the last time, we were just we want the marginal of x2, and we were just writing out the first. Yeah, we were writing out these messages, right, a few pages ago. Now let's look at this, right? So, well, p of x is basic product of these three factors. Now, instead of using x2 as a root, let's use something different, x3 as a root. As you can see, x2 as a root was the simplest because, right, it's depth 2. If we use x3 as the node and we shake it, well, yeah, basically hold this whole graph by x3, it's depth 4, right? So it has 4 different edges before we reach x1 or x4, right? So let's work on this more complicated case. We initialize the graph from the leaf nodes x1 and x4. Let's see, leaf, and this is a leaf, right? Right. Therefore, for the initialization, the leaf message is from a node. It's just 1, right? And now we and this message is sent from x1 to fa. No, which one is right? And this one is fc, and this one is fb, right? And now, okay, we're done with one level of I guess edge already. That doesn't seem too hard. And now let's look at the message from fa to x. So this is the one where we don't simply multiply. We multiply the message, we then multiply the factor, and then we marginalize. That's what we do. So it's the product of mu of the x towards fa, right? So this term is 1 because it only has one incoming message. We multiply with the factor, and then we sum over essentially the grandchildren node, which is x1 in this case. All right, we know how to do that. We do the same for the X4 FC X2 branch. And now we do a node to factor message again, which, as we have defined, is simply the product of these two, right? So this is mu of FA to X2, mu of FC to X2, right? So we simply multiply these two. So that's the node to factor message. That's easy. And then we get a factor to node message again. We do this more complicated thing. We take the node to factor message, multiply it with the factor, which is f of b, and then get rid of x2, which we don't need. And the end of this is, right, so note that this is a function of x2, right, multiplied by a function of x2 and x3, and then we essentially marginalize x2 out. So this factor, so if we sort of think about f of b as unnormalized conditional probability table, like k by k table, and x2 is basically a modulation factor on each row if we put x2 on the rows, right, across the rows. Right. All right. So hopefully this helps. Now there is, right, the flow of the sum product algorithm, and we can, yeah, this next picture is basically, we can also compute the flow of messages the other way around. You might ask, why do we want this? Well, A, it's defined the same way, and B, by doing this, we can actually get all the marginal probabilities and even some conditionals by doing this. Meaning that we don't have to do the sum product propagation again if we all from scratch for each and every marginal that we compute. If we compute all of the messages in both directions, the claim is that if we want, let's say the joint probability of x2 and x4, we can just get it. I will just leave you with the claim and for now. But basically, let's just have a stare at this messages of the other direction. We start from x3. We start from 1 again. And we'll do this multiply by fb and sum over x3. We get this next message. And then we simply multiply by fb to x2 and fc to x2, which is this one that we already have. Okay, so we do need the messages we got. We computed in the last page, right? So this is like fb to x2, and this is fc to x2. And now we get x2 to fa. And then the fa to x1 is multiplying fa and marginalize over x2. So this one will allow us to easily get the p of x1, right? Similarly, this one will allow us to easily get a p of x4. So if we compute messages in all messages in both directions, we can, like, we get all the marginals. Indeed, this is what is happening. So, and as we walked over in the previous, like an example about 10 pages ago, the marginal probability of x2 is also like easily obtained using actually 3 of these product of the 3 messages because it's connected to 3 factors. So once we have this, we have all the messages we can just pick, right? We pick basically all the incoming messages coming to X2. So that is to say, we pick this message, and we want this message, and we want this message. And these are the 3 times we multiply to get the marginals of X2. So now that looks very useful, and I hope you are by now somewhat convinced that this sum product recursion is a good thing. So this mostly, so this is all the procedural and the recursive part of this lecture. Now let's just do a bunch of talking to reflect on what we have learned. Right. So the goal is to find some marginal and try to marginalize away all the other variables. The idea is we interchange summations and products using elementary school math. So we push sums as far into the product as possible, meaning doing the sums as early as possible, because in these big long equations, we actually compute from the end. And we view partial sums of messages, and they're coupled by factors, and then we're dealing with these coupling by propagating messages. And messages are actually functions of some variable. We always keep that in mind. Messages are always functions of the clique, and when they're marginalized out, some variables of those clique are, especially those ones that are downstream, or like depending on which direction we're going, the ones that are downstream gets marginalized out. So, and why are we working with factor graphs? We exploit the tree structure of the factor graph to divide and conquer. So the tree structure helps us to see which sum we can push as far as possible and how far we can push it. So the tree structure is crucial. If we do this sort of sum product, it's generally incorrect for loopy graphs. Despite we can do this, there's not much guarantee. Sometimes doing so is useful. Let me just say that. So the approach has many names because this is like relatively recent research. It's known as belief propagation for DAGs, for base nets, message passing, and sum product algorithm. So our book adopts this, mainly uses the sum product name. All right. So we more or less covered this already. If we do a brute force, we run the above algorithm for each node. Oh, that's not very good. The more efficient way is to arbitrarily choose some root in a graph. It doesn't matter which one we choose, as long as the factor graph tree is the same, the computational complexity is the same. And we can propagate all messages from leaves to root, and then propagate all messages from root to leaves. And then we just pick the right combinations of messages to get all the marginals. So as we saw from the example, this only doubles the number of computations rather than having to do it n times. All right. So we're just gonna do a bit of hand waving and talking to say, now that you know sum product algorithm, you can know max product. So there are actually pretty good, pretty cool math behind this, right? So this paper actually coming out around the same time as the sum product algorithm paper in the same journal, Attribute Transactions on Information Theory. It says it spells out this generative distributive law. So meaning that in this distributive law that we learn in elementary school, the not so elementary part is we can replace sum and product. So you could do max product, such as you can do max of AB and AC, buying some conditions like A needs to be non-negative, is sort of max B or C times A. Okay, better write it the same way. A times max B and C. Well, if A, B, C are probabilities, these are like, yeah, generally true. So this is exactly what like max product tries to do. So the abstract theory is the sum and the multiply, they are sort of, they satisfy this distributive property called the semi-ring. I won't go into that, but like to be fully general, you need to know a bit of algebraic theory. So this is exactly what we wrote on the last page. So what we did is we replaced the sum by max and then replace multiply by actually sum. Then this allows us to do what's called decoding. For hidden Markov models, this is called the Viterbi algorithm. So there is a chapter on sequential models in chapter 13, where the discrete version or discrete state version is called hidden Markov models, which is a direct application of this max product or sum product algorithm, which we will not cover this year. We did spend time on this last year, but that means we were not covering other things such as generalization. I feel like once you have learned the language of graphical models, graphing HMM when you need it is good. That is also to say, I'm not going to hold people responsible for hidden Markov models in the final exam. Hope you're happy to hear that. So let me just make a note about this max product is super useful. So the sum product is useful for inference and learning parameters. The max product, well, this decoding kind of operation is actually being done all the time, right? So for example, speech recognition, as we have covered, sometimes there's multiple layers of these, like such as from sound to words to sentences, and then language modeling. NLP is all the rage in, I guess, ML deep learning. So like basically what are sentences, or that consist of tokens. Also communication. Let me just say wireless communication, whether it's Wi-Fi or your like mobile phone. It doesn't have to be wireless, right? So radio. Basically under noise, under corrupt atmosphere and transmission, under channel transmission, what was the like digital message that were originally sent? As you can see, these are like a much lower layer, but fundamental layers of communication that were guaranteed by operations like this. Yeah, if we first have to make sure that the binary bits are correct before we decode, sounds and words and so on and so forth. And this applies to anything we send, text messages, images, SMS, with like video to our family and so on. Yeah, there are many other fascinating applications. So let's also just talk about two other related terms on inference. There was this junction tree algorithm that performs exact inference in generally undirected graphs. So for base nets, like with the routine is first convert to Morrow graph, and then essentially I would call it make clicks in the way that when there's a 4-node circle, we essentially make clicks by making new edges, by making a click. And then each click is turned into, like, then we can convert the resulting graph, like undirected graph, into a tree of clicks. It's called junction tree because it's a tree of clicks. The way of constructing this tree is quite neat. It's called maximum spanning tree. That is the efficient algorithm. So basically, we connect the click with its most the other click with most number of overlapping nodes. And the inference is generally sort of scales exponentially with the size of the maximum click. The same can be said about factor graph. But this junction tree machinery is mainly used for Bayes nets, because as you can see from the language. But factor graph, it can be used for general Markov random fields. It's the same computational complexity. It's also to say that moving among the these different terms, belief propagation, junction tree, sum product algorithm, factor graph, the computational complexity is the same. There's no free lunch there. If you, for example, if the maximum click size is too big, then you could resort to various other things, such as approximate inference, sampling, and so on, to make it doable. We won't have time to cover this in the current semester. I would say those requires maybe a week or two of proper treatment on their own. So then let's say something again about loopy belief propagation, or what if factor graph have loops? So basically, this term loopy belief is that we can just try some product algorithm and graphs which are not tree structured. But when things are not tree structured, we can basically create messages and propagate them using exactly the same algorithm. The graph has cycles, and then information flows several times through the graph. There is no longer the notion of one forward pass and one backward pass and we're done. If we do the forward pass first, then the backward pass will depend on the forward pass, and then we can do another forward pass, then the message will change again. So that's what you meant by information can flow several times through the graph. So we can initialize by essentially assuming a unit message. Then what this means is that the convergence is no longer guaranteed in general. We can still do this, but we might not get the correct marginals. We might still get useful information. So that's that. That's pretty much it. The table of contents is really short. We defined factor graphs. We looked at some product algorithm in some detail and with an example over again. We did a bunch of talking of the properties of some product and related algorithms. So that's all of today's content. And now you know most important things that needs to be known about graphical model. Any questions? No. So hopefully people are all feeling sort of you've learned something. And hopefully silence doesn't mean that people are all still confused. Yeah. Yes, it's a little bit abstract, but yeah, looking at it again, hopefully will help. And the lab session should help. Basically, the lab or the role of the lab is to get people used to manipulating these factors or messages as functions, or as in the discrete case, as probability tables, or like not necessarily probability tables, but just yeah, tables of values where we multiply and sum. And at the end, it somehow comes out correct, which is great. If there are more questions, I think we should, yeah, wrap. And hopefully I'll see lots of you on Wednesday person. We're in Fifth T again. Right. Bye, everyone.